I want to try to install C++ OS on this computer. It features a whopping 512 kilobytes of RAM, 128 kilobytes of read-only memory, and a 25 MHz 486SX. The real-time clock in the programmable interval timer doesn't work because I wired it up incorrectly. It also uses an 8-bit system bus, not a 32-bit bus like most 486 motherboards. It doesn't have any ISO slots, it has these instead. I'm just going to call them simplified low pin count slots or SLPC slots. It kind of doesn't matter either way because you can't buy these anymore, so I'm going to not use them in any future designs. Or at least that's the plan. The V9958 of course took some finagling to get this to work on a x86. Basically, the V9958 latches its write data on the rising edge of the write signal. So I made the FPGA modify the write signal to pulse in the middle of a clock cycle instead of being asserted the entire time while the V9958 is being selected by the host system. This solved most of my x86 V9958 issues, and I think I could squeeze a little bit more speed out of it if I tried, but that's for another day. C++ OS works best with a data storage of at least some kind, so I need to figure that one out. Alright, fine. I'll see if I can get this to work. It's basically a XT IDE but worse. It ain't much, but it's mine. In order for this thing to actually work, first I have to make a driver for my 486 motherboard's BIOS. I converted the Z80 assembly code from when I did the same thing, but on a Z80 computer, into x86 assembly. All things considered, this part wasn't too difficult. I wish everything could be this easy. The next thing to do is to make V9958 drivers for C++ OS. Unfortunately, then I started having problems with the reliability of the ROM socket. I could have fixed this, sure, but I decided to build a better computer instead. Believe me, this new computer is so much better that it's gonna be worth the wait. Let me take a minute to explain how it works. So there's the CPU, and I want to use a 32-bit data bus. A 144-pin FPGA doesn't have enough pins, so for this build I need to use 2 of them. Using 2 of them makes the PCB more complicated, but it's still cheaper than using one big expensive FPGA. Each FPGA handles separate smaller tasks. The only exception is the DRAM, where FPGA 0 has to generate the RAS and CAS strobe, the DRAM row and column address, while FPGA 1 does everything having to do with the DRAM's data bus. I don't know if this is even going to work, but I also have 2 megabytes of SRAM on the motherboard just in case it doesn't. The SDRAM has a 64-bit data bus, while the 486 CPU only has a 32-bit data bus, so FPGA 1 has to handle bank swapping. I may end up finding a way to make contiguous 32-bit reads twice as fast if this actually works. It's probably still simpler than setting up that L2 cache system that Intel talks about in the datasheet, but it's still really complicated. I'm still using a dedicated PS2 controller chip. The VT8242N just works pretty well. Hopefully it'll be possible to set up that USB 1.1 port with 3.3 volt logic levels and get an FPGA based keyboard controller someday. If I'm going to keep building ever more complicated computers, I need to start doing more with FPGAs and less with these arcane weird chips. Once I got the power regulator circuit for the FPGAs on there, I checked the voltage and got 1.2 volts. That's good. So next I put the FPGAs on there. I checked to make sure that they worked, and then I started on the CPU socket. After that, I did some more testing. I added more of the CPU capacitors, I added more chips, and then once I was pretty sure that it wasn't going to catch on fire and explode, then it was time to insert the CPU. And this officially marked the beginning of the fix everything I did incorrectly phase. Mainly I wired up these chips with a 5-volt connection instead of a 3.3 volt connection. That was an easy fix. Also, I forgot to add SPI ports for each of the FPGA ROMs, so I just use wires instead. It works. This one's pretty annoying, but it's not annoying enough to get a different circuit board, so I'm just going to keep going with it. But will it work on the first try? Let's see. So there's obviously a lot more going on here than what you see. I eventually found a pin on a chip that wasn't connected. After I fixed this, I was able to get the CPU to properly execute a halt instruction. So when the 486 CPU first turns on, it reads the next 16 bytes of opcodes, and after reading all of them, then it begins to execute them. So you can see how it read all 16 of them, and then it stopped. That means that it halted. Next it was time to try a Hello World. So I loaded up a Hello World program and then ran it. This almost worked, but the screen kept doing this. For some reason, the delay I was using wasn't working, and it was writing to the LCD screen too fast. I thought this was a problem with the bus steering logic in my Verilog code on FPGA 1, but it turned out to be something else entirely. I noticed that it didn't always send commands to the LCD screen at the right time. When this happened, it kept sending commands to port A800 instead of A000. It turned out bit 19 on the data bus was bridged with another signal. This meant that sometimes when the CPU was reading the opcodes off the ROM chip, the bits would be aligned in such a way that it would read that IO address as A800 instead of A000. Against all odds, I managed to fix this problem without having to take the chip off of the circuit board. I tried it again and it actually finally worked. So now the 486 CPU can read program data off of the ROM. That doesn't mean that it can access the RAM though. This is the assembly subroutine that I use for making sure that the LCD screen is ready before sending data to it. This is how that subroutine is used before sending data to the LCD screen. In x86 assembly, call and return instructions involve the stack. This means that you can't use them unless you have functioning RAM. So I tried things like that, and wouldn't you know it, it didn't work. I then found out that my Verilog code on FPGA 0 was enabling the ISA bus for exactly 1 clock cycle at the end of every memory write cycle. This was corrupting RAM because it would cause bus contention during the exact moment that the SRAM chips were supposed to be saving the contents of the data bus to the memory location on the address bus. So I ended up changing it to this instead. It seemed like the right thing to do, at least on paper. I tried it after that and it worked. I even added some more complicated subroutines that use the memory a lot more, and it still worked, and it was even more stable than before. There is still one more final memory test it has to pass before I can do anything more complicated with it. It needs to be able to copy the ROM data to the RAM, jump to that data, and then be able to execute instructions directly off the RAM. This is going to involve such a relatively large number of clock cycles and memory operations that if I can successfully get that to work, I'll know that I have an absolutely rock-solid system. At least at 8 MHz. It didn't work at first, but you know that problem I just fixed with the ISA bus? Well, I had to do basically the same thing to the front side bus. I expect I'll have trouble with ISA bus write cycles when I start plugging in ISA expansion cards, but I'll just have to wait and see. And that ended up working. So then I tried it at 25 MHz, and then it still worked. Now it's time to get the keyboard working. Normally this PS2 keyboard circuit I use is really reliable, but I couldn't get it to initialize. I checked the documentation and it turns out that pin 7 is supposed to be connected to ground. It turned out I had this exact same problem on the 8-bit 486 motherboard, so I fixed it and then forgot about it. The VT82C42N, gosh what a mouthful, is probably the best all-around PS2 controller. It needs fewer supporting components than the HT6542B, which is also one of the best just because it works with a PS2 mouse. The original 8042 isn't really worth messing with because it's even more complicated to set up and it doesn't even work with a mouse. So anyway, I added a bodge wire connecting pin 7 to ground and then the keyboard controller started working. You know what this means? Now it's time to get a video card. The ICE 40 16-bit video card to be exact. I still have it only half working, but this new 486 motherboard is the perfect, most ideal possible test platform for it. Not having to sit through an obnoxiously slow award BIOS boot screen followed by MS-DOS verifying DMI pool data like it's billing by the hour is going to save so much time that it will be worth all this effort. Now it's time to start trying to get the video card working. There's no way it's going to just boot up and work on the first try. The settings register is at IO port 423 hex, so I tried reading that. Doing this returns FF, which is not the 70 hex that it initializes to upon reset, so I know that there's something wrong somewhere. Oh wait, actually, turns out I just forgot to enable the 16-bit cycles over the isobus on my 486 chipset. On x86 computers, most of the time when there's a 16-bit data bus, even address 16-bit access cycles use the entire bus. Odd address 16-bit cycles are converted into 8-bit cycles that use bits 8 through 15, while 8-bit cycles use the lower 8 bits regardless of address. Fixing this meant incorporating the 486 BS16 pin onto my chipset logic. This was the first time I ever did anything with the BS16 pin, and it worked on the first try. I still have to fix all the problems with the video card though. I found this thing called Verilator that can be used to simulate Verilog code with C++ programs. I then used SDL to make a virtual monitor and then a random number generator to simulate uninitialized VRAM. This resulted in a very slow but highly accurate simulation of most of the logic that runs the video card. I can write data to the screen over the simulated isobus, but more importantly I can more or less simulate the snow issue I keep having. It ended up being too hard to make the Verilator simulation behave the exact same way as the hardware, but I still had one more debugging tool to try, and that is rubber duck debugging. That's where you just think about it really hard while optionally pretending to explain it to a rubber duck until you realize what the problem was all along. And eventually, against all odds, I finally got it working. It's still slow, and there's tons of room for improvement, but I can actually use this for stuff now. If you really want to know more details, you can go on GitHub and look at the code. Next, I had to figure out how to actually boot C++ OS on this thing. In the interest of time, I decided to just put it on the 128 kilobyte ROM instead of build a whole multimedia card first. When an x86 CPU boots up initially, it starts in 16-bit real mode and begins program execution at this address. In x86 real mode, addresses higher than this number, or 1 megabyte, are blocked from being accessed except for in this special 64 kilobyte segment at the top of address space, which the CPU loses access to completely after executing a long jump instruction. This means that memory can't be accessed until the computer switches into protected mode. However, C++ OS has a binary size of just under 128 kilobytes, taking up not one but two real mode segments. This is what you would call a bit of a pickle. I can't just put C++ OS into RAM without switching into protected mode first, so I had to make a multi-stage bootloader. First, I made a 256 byte segment that copied a 512 byte memory copying program into RAM at address 8000. That memory copy program then switches into 32-bit protected mode and copies the entire contents of the 128 kilobyte ROM into RAM at location 10000. Then it jumps to memory location 10000, which contains an assembly program which then jumps to wherever the location of the C++ OS begin function is. I finally got that working, and boy is it slow. Also, the video card started running like crap again. I'll have my work cut out for me in the FPGA video card part 3 video. A lot of this slowdown is just because I'm using a 486SX. It stores the font data as 1 bit per pixel, and then it converts each character to a 16-bit per pixel 8x8 sprite before sending it to the video card. So I would expect this to be slow, but wow, it's slow. I'm sure I will eventually get to where I can do some interesting stuff on it. Maybe after I optimize the video card, fix the rest of the issues, and try a faster CPU, things will start getting good. Until then, that's all I got for this video. It took a long time to even get things to this point. That's all I have for today. Thank you so much for watching. If you want to help support future development, consider buying me a coffee. Thanks, bye.